Now let's continue on motor characteristics. Here we have separately excited DC motor, and here is the shunt motor connection. Let's write the equations. For example, field voltage terminal equation is RF times field current makes field voltage. Here is RF a symbol. In fact, in this case, for example, RFC field controller rheostat plus RF winding. Whatever it is, I mean the total resistance here. Total resistance of field circuit times field current makes terminal voltage. You can write Kirchhoff's voltage law around this loop. So induced EMF here inside the armature. Here's the resistance. Here's the armature current. Here's the load current. But that is motoring. So current is entering. That is the, let me correct this. You'd better draw like this. So applied terminal voltage will be equal to summation of the voltages around the loop. Resistance times current here is the resistive voltage drop plus armature EMF is the terminal voltage, and it is given here. And there are two basic equations. Those are EMF equation and torque equation. Armature torque is equal to Ka times flux times armature current, and that is the mechanical speed of the shaft, omega, and armature EMF induced in the armature. In the shunt side, it is almost identical. Again, field voltage. In this case, it is special, not an external field supply used. Here we excite the excitation circuit from terminal voltage, armature terminal voltage. This resistance, in fact, inside the EMF. Let me show. I have used some ready drawings, so yeah, there is something different, but there's no problem. There is nothing new. Here, this is the machine operated as motor, and it is said that it is shunt. Okay, here's the shunt winding. That's it. Here are the electrical terminals. You apply some electric power from the terminal, for example, by using some batteries. Here's the terminal voltage supplied by battery. Here's the load current. Here are two branches. One is field current, one is armature current. That is motor operation. Here's the mechanical output in terms of torque and axis, yani angular speed of the shaft. Okay. There's a noise out of my room, and it disturbs me. The equations are identical, but only field voltage, instead of separate field voltage, we excite machine by terminal voltage, and all the others exactly the same. But Here's load current is equal to armature current in separately excited machine. Here's load current. Here's armature current. Those are identical. But here is a Kirchhoff's current law for these nodes. Kirchhoff's current law applied load current will be divided into two components. Like this. So armature current is equal to load current minus field current, shunt field current. That means you should draw a connection diagram, and then you can imagine equivalent circuit of the related connection diagram, and then write voltage and current laws. Okay, here are the equations for motor operation, and then let's talk about terminal characteristic. Sometimes it is called as torque speed curve. It is terminal characteristic of motor. Earlier I said, what is the output? Output is mechanical power. What are the multipliers? Multipliers are torque and angular speed of the shaft. That is across, that is flow parameter. So across parameter versus flow parameter is called as terminal characteristic. Sometimes in the sector it is called as torque speed curve. Torque speed curve or characteristic. Here in this case, for example, I have given the relation in terms of angular speed. But in the sector, industry, many times it will be easier to understand RPM speed. So it can also be given in terms of RPM speed. The relation will be similar. Let's talk about the relation. Okay, gentlemen, let me talk on shunt motor, for example. It makes no change. Let's just talk. Terminal voltage is equal to EMF plus current times RA. And then, you know, EMF is equal to something like this. And let's substitute EMF here. Let me do it. Vt is equal to Ka flux omega plus current and RA. And then let's calculate W. W is equal to Vt minus RA times current over Ka phi. Here's current. Here's angular speed. You got it? You got angular speed. Here it is. But you need torque. But it is not in this equation. You know torque is equal to Ka times flux times current. Instead of, let's take current. Current is equal to torque
divided by
Ka phi. And then substitute it here. Vt minus RA, instead of current, substitute the torque equivalent. Torque minus Ka phi. Houston, here's another one. Okay, square, but here's one. That is the relation in this box I have already discussed. What it looks like. It looks like a first order linear equation. Y is equal to minus mx plus a. It looks like something like this. Here is a, here is y, here is x, here is the slope of the linear relation. That is the slope. That is the theoretical result coming from these equations. It starts from no load speed, theta. Let me take it here again. This guy, omega mechanical is equal to something constant, omega naught. When there is no torque, let's say substitute 0, that is no load speed. No load speed is equal to Vt over Ka flux. That is omega naught minus a coefficient times torque. So speed starts from an initial value and drops linearly. That is the slope of the curve. Here's the torque. It looks like this. Slope is given here. That is Ra, resistance of armature. Now, here are two different machines, for example. One has got an increase in resistance. Slope will be different. Okay, let me add another extra rheostat here. When you increase rheostat, slope gets larger. With Rx, Houston, you see the effect of resistance. Resistance causes a change in slope. What about the no load speed? Theta, Houston, no load speed comes from terminal voltage, mainly, looks like. And when there's a voltage change, there will be some no load speed change. It looks like, but take care. What about flux? Flux is equal to, is a function of field current. Let's say a linear function of field current. Field current is a function of applied voltage. Applied voltage over some resistances around this loop. Let's say volt R, that is the total resistance in this field circuit. That is a field current. Here's a linear coefficient to calculate field. And then when there is a change in field voltage, Houston, for example, when you increase this, flux will increase. Theta, speed will be constant. Looks constant, but in reality, you know, there's a saturation. If you increase terminal voltage much more, flux cannot be increased properly. When you increase field current, flux will increase, but that saturates. Theta, when you increase terminal voltage dramatically, after a certain point, there is no increase in flux. So flux will not increase. After a certain point, is no load speed starts to increase. When you increase terminal voltage, here, no load speed will increase after a certain point, after saturation starts. Okay. Let's discuss. Let me make another discussion here. What about permanent magnet DC motor? Okay. Let's write the equation, clone the equation here. The relation was this: angular speed is equal to Vt over Ka flux minus Ra over Ka flux squared times torque. Okay. We were discussing permanent characteristic or speed torque curve, torque speed curve. Houston, in permanent magnet DC machine motor, flux can be assumed constant. Generally, it is given constant, but you know, there will be some armature reaction, but it is a bit complex. It cannot be easily modeled. Okay, let me talk about in permanent magnet machine, Ka times flux can be assumed constant, just like what it was in third quiz. You remember, it was given Ka phi constant at a certain value. Let's say gamma constant. So angular speed Vt over gamma minus, here's gamma square Ra minus gamma squared by T. But again, this is also another coefficient. Let me say zeta W is equal to, omega is equal to Vt over gamma minus zeta times T. Houston, let's draw this. That is, excuse me, that is the no load speed. That is the slope of the curve. That is torque, angular speed, starts from no load speed, and then here's the slope. That is the speed, torque speed curve of permanent magnet DC motor. And in this curve, when you change voltage, let's say that is V1, V terminal 1, and then let's decrease V terminal 2. That is the speed curve for another voltage, terminal voltage 2, which is less than terminal voltage 1. That is the no load voltage for the second case. Houston, here would be some parallel characteristics with respect to voltages. When you change voltage, a torque speed curve will be smoothly relational. There will be some relational changes. The characteristic would be like this: start, blah, 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 blah. Slope is the same, but the starting or no load speeds will be changed due to terminal voltage, because it depends to terminal voltage. When you change terminal voltage, it will changes. But this method, that is a speed adjustment method, in fact, is generally used underrated voltages, underrated speeds. For example, you generally drop terminal voltage because a machine perhaps cannot stand over voltages. So let's say machine has a rated value of 220 volts terminal voltage, and then you can decrease voltage, but you cannot increase. It is not permitted to increase voltage. Perhaps there will be insulation failure. So we generally use such a method for the speed adjustment below rated speed. You decrease voltage, speed will decrease. So we use such a adjustment method for underrated speeds. Underrated speeds. For example, let's say rated speed is 1500 RPM. So you can decrease voltage and you can adjust speed between 0 to 1500 RPM. Aha, that's it. Remember your toys when you are a child. If there is a decrease in battery, your toy will slow down. So that is the relation. Toys machines are generally permanent magnet DC motors. So when there is a decrease in terminal voltage or battery voltage, so resultant speed will be decreased. That was the extra discussion on permanent magnet DC. What about series motors? It is a bit complicated and unique, very unique characteristic, very important. Okay, let's draw the connection diagram. That is the equivalent circuit. Let me draw it here. Here's the armature motor DC. Let's say A1, A2, those are armature connectors or terminals. Here's the serial field coil. Let's say serial 1 and serial 2. Those are serial terminals. And here are the main terminals for the power supply. Here would be a power supply or a battery delivering some power, electric power, and this machine will convert it into mechanical power. That is motor. And now let's draw the equivalent circuit. Here's armature circuit, plus and minus EMF. Inside the armature there is a resistance of armature winding, and then here is serial connected resistance. It is not compulsory to draw these resistance here because this is not a connection diagram. It is just a equivalent circuit. Here is resistance and here is the terminal for the power supply. That is the load current entering the system. That is the field current passing through the field coil. That is the armature current entering the armature. All those are identical. Of course, here would be some extra resistances in the circuit for control purposes, but they are not given here. You know the main terminal equation or definition. There is another, torque, armature, induced, Ka flux, armature current. Those are two main equations defining DC machine behavior. So, here's the Kirchhoff's voltage law. Applied terminal voltage is equal to current times Rs plus Ra. RS plus RA. Let me write armature current. It can be equal to field or load current. It doesn't matter. And then here is EMF. Houston, armature EMF. Then we'd like to get torque speed curve or speed torque relation. Here's the speed, here's the torque. So we want to find out this. So I solve armature EMF. That's it. That is the armature EMF taken to the left. Vt minus current times blah blah resistances. It is given here. And then you know the equivalent. You know the current equation, and if you neglect saturation, field versus field current relation, it is something like that, you know. It starts from here, turn back to here. Let's assume that it is a very linear relation. The coefficient is K1, neglect saturation, and remanence flux, and phi r is neglected. In fact, it would be here if you not omit or neglect phi r, but the equation will be much more complicated, so that is not required right now. Understanding the basic principles is important, so we make some simplifications. We omit something. Flux can be written as K1 times field current. Field current is equal to armature current, so that is the linear relation of current. Then I can substitute flux here. Induced EMF, Ka times flux. Let's substitute the equivalent one, K1 times Ia. And then here is omega. Houston, here are two coefficients. Let's define a new one. Ks, series coefficient. You should not know this. This is not important. The relation is important. The figure is important. Ks is defined by Ka times K1. We have earlier defined. So here's the coefficient, current, and angular speed. That is the EMF. And then I can substitute this guy into here. That is the equation. Omega on the left and Ks times armature current is down to here, and here is something missed. Current is eliminated, and then here's only Ks. Houston, in the equation everything looks good, but there is nothing as a function torque yet. Where is the torque? I wanna find out torque relation. So here's current. Torque, you know, torque is as a function of field and current. So Ka is here. Instead of flux, you substitute K1 times Houston, here it was, K1 times current, here it is, but here's another current, so here's armature current squared. Those two coefficients together make Ks. Ks times I squared. Houston, torque is equal to Ks times IA squared. So, Houston, here is armature current. So let's calculate armature current. Armature current is torque over Ks. Was it? Yes. Torque over Ks, all in square root, or something like that. Yes. Okay, let's substitute it here. Armature current. Armature current is already calculated here in terms of torque. Let's substitute the equivalent down to here. So final equation will be like this. It's the final equation.
What do you see in this equation?
Houston, it's a bit complicated. For example, if torque is 0, hatta omega mechanical tends to infinity. Houston, yes, it is normal in this machine. This machine shouldn't be operated without load. If torque is 0, no load, no load, no mechanical load, that is motor, speeds go up to infinity. Let me show you. Here's another, here's a series motor. That's called as pull out. Kaçıp gitme şeklinde söyleniyor. Let me find DC machine playlist. I hope the movie is here. Yes. That is a washing machine motor. It is an AC motor, but the principles are coming from DC machine. That machine is designed for AC operation. So, you know, AC, there are higher rate of iron losses. So here you see body is not cast iron. That is silicone sheet material, not cast iron. So such a machine called as a universal machine, universal motor, is a kind of series motor designed for AC, universal motor. Those kind of machines are generally used in our household devices, especially can operate over 3000 RPM. Now, there is no load. That is the shaft on the left, you see. There is no load, ladies and gentlemen. First, take care. We apply electric power without there is no load, when there is no load. And then, you please listen, sound of speed. It is increasing. It keeps increasing. It is still increasing. Still increasing. It continues. It is still increasing. It's still increasing. There's an electric failure on commutator brush system due to overspeed. Now, this machine, if operated without load, the machine will be damaged. The speed will increase up to there is a damage. Result is always damage. There is an electrical or mechanical failure. What is the good side of this characteristic? Now, ladies and gentlemen, take care. In startup, there is no speed yet. This machine can produce extremely high torques. Ta-ta! That is the most important thing for a motor. Remember, Newton's equation, torque motor minus torque load is equal to J dW over dt, that is the angular acceleration. In case here is friction, here is another terms, that is a differential equation. Acceleration is a derivative, so in steady state, there is no speed change, so in steady state, applied mechanical torque will be equal to log torque, but in the startup, you should start machine from 0 speed up to, let's say, rated speed. To manage this, let's say angular acceleration alpha must be positive to increase the speed. Angular acceleration must be positive. To have positive acceleration, torque motor must produce much more torque than low torque, Houston. So, in heavy loads, just like trains, locomotives, electric cars, forklifts, and some heavy instruments, drills, for example, we use serial type motors. For example, for starting purposes in our cars today, automobiles, we use serial DC motor to start up inner combustion engine. That is the starter motor of everyday automobiles. Okay, serial characteristic is very unique characteristic. It yields highest torques ever than the other motors. But there is one adverse property. Such a machine cannot be operated without load. Otherwise, result will be a failure or damage. Machine will be distracted, as you see in the video in my playlist.